Inside every factory, we have an invisible conversation that is constantly taking place. There are always machines exchanging information continuously. Sensors are reporting measurements, controllers issue commands, and supervisory systems actually aggregate the results. Yet, these machines were not designed in the same era and by the same vendors or for the same purpose. And as a result, they communicate using fundamental different protocols. Three of these protocols dominate the industrial landscape today, and I'm talking about Modbus, OPC-UA, and MQTT. Understanding how they differ and how they work together is really essential to understanding how a modern factory actually functions. This episode examines each protocol in turn, then explains how they operate as a coordinated system. Three of these protocols dominate the industrial landscape today, and I'm talking about Modbus, OPC-UA, and MQTT. Understanding how they differ and how they work together is essential to understanding how a modern factory actually functions. This episode examines each protocol in turn and then explains how they operate as a coordinated system. So Modbus was developed by Modicon in 1979 to enable communication between programmable logic controllers, I'm talking about PLCs, and then field devices. It is by a significant margin the oldest of these protocols and is still in widespread industrial use. Its design reflects the constraints of this era. It operates on a single request-response model. So we have a master and the slave. So the master queries the slave device for the value held in a specific register, and the slave returns the value. The protocol carries no metadata or no security layer or no description of what the data represents, just raw values. The register may contain maybe temperature, pressure, or maybe a status flag. The interpretation is left entirely on the engineer integrating the system. Yes, and that is some of the constraints that Modbus comes with. So despite these limitations, Modbus remains deeply entrenched across the industry. Some sensors or a lot of sensors still support Modbus. It has been running for the past 4 decades. So its longevity is a function of three qualities. The first is the fact that it is very inexpensive to implement compared to other protocols. 2, it is exceptionally lightweight. And 3, it has proven reliability across 4 decades. So for the past 4 decades, Modbus has proven itself to be very reliable. And these three qualities is what makes Modbus still being used across industries in the world. Modbus represents the foundation of which much of today's industrial infrastructure still rests. The next is OPC-UA. So OPC-UA just stands for OPC Unified Architecture, and this protocol was released in 2008 by the OPC Foundation. It was designed to address the structural deficiencies of earlier industrial protocols like Modbus. Where Modbus transmits raw values, OPC-UA transmits information. Yes, real information. I'm talking about values that is accompanied by context, metadata, and semantic meaning. So in an OPC-UA exchange, a device does not merely report a number. It identifies itself, declares the type, and then the unit of measurement. It references its position even within the hierarchical information model. It can go further to authenticate the request using built-in cryptographic mechanisms. So example is a motor controller that can expose not only its current speed, but it can also expose its operational limits, maintenance history, manufacturer certification, all in one machine-readable form. And that is the beauty of OPC-UA. So OPC-UA is a platform-independent protocol. So that means that it doesn't depend on one specific platform or one specific vendor, and it is engineered for interoperability across heterogeneous systems. What this means is that you can have Allen Bradley machines, you can have Siemens machines, and they communicate to each other via OPC-UA. It doesn't have to be all Allen Bradley or it doesn't have to be all Siemens. These two different industrial equipments can communicate to each other through a standardized protocol, and that is OPC-UA. It supports both the client-server architecture as well as the publish-subscribe communication patterns, and it operates securely over modern network infrastructure. So these properties have made it protocol of choice for Industry 4.0 initiatives. Whenever you hear about Industry 4.0, one of the protocols that is widely used is OPC-UA. So So even when it comes to digital twin implementations, integrated manufacturing operations management, all these, we have OPC-UA being standardized industrial protocol. So one of the trade-offs of OPC-UA is the fact that it's computationally heavy to use. So OPC-UA requires greater processing capacity and configuration efforts than an older model like Modbus, which limits its use in the most resource-constrained edge devices. So you want to take data on a Raspberry Pi. If you have to choose between Modbus and OPC-UA, you definitely might go for Modbus, simply because OPC-UA requires a lot of computation, and then you're working on an edge device like Raspberry Pi. You have to make sure that you are utilizing the resources really well. Then we move on to MQTT. So MQTT, that is Message Queuing Telemetry Transport. So this was developed in 1999 by IBM and CyrusLink for remote monitoring of oil and gas pipelines. So its objective was to be able to reliably communicate over networks with limited bandwidth and intermittent connectivity issues. MQTT introduces a different communication paradigm altogether. Rather than just a direct request-response exchanges, it employs a publish-subscribe model coordinated by a central broker. So we have the central broker, and you imagine the central broker as a post office. So the mailman publishes it, and then another person also takes it from the post office and then delivers it. So it uses the publish-subscribe architecture. You publish the data to a named topic. Any system subscribed to that topic receives the message in near real time. Publishers and subscribers do not need to know one of each other's existence. So the publisher doesn't know that the subscriber exists, and so that the subscriber doesn't know that the publisher exists. This decoupling, combined with the protocol's minimal footprint, makes MQTT exceptionally well suited for large-scale telemetry. You can have a single broker that can support thousands of devices, each transmitting small payloads efficiently. So for this reason, MQTT has become the standard transport layer for industrial Internet of Things deployment. It is connecting field-level data to enterprise and cloud systems effortlessly. That is what has made MQTT popular among Industry 4.0 and Industry 5.0 projects. So MQTT, just like Modbus, is agnostic to the meaning of the data it carries. It is a transport mechanism that is very efficient, scalable, and then it's protocol neutral. Then we move on to the integration phase. Before we continue, make sure you hit the subscribe button and like this video if you learned something new. All you have to know is that in practice, these protocols are rarely treated as alternatives. They are deployed as complementary layers of a single architecture. So you don't just decide on one, but you only use it when necessary and when you are dealing with a specific equipment. So a typical industrial data flow may begin with a legacy sensor communicating over Modbus to an edge gateway. And then you have the gateway that translates the raw Modbus registers into a structured OPC-UA nodes, enriching the data with context, units, and identifiers. So the structured data is then published via MQTT to a broker, from which it is distributed to historians, analytic platforms, and even cloud-based dashboards. Each protocol communicates a distinct capability. Modbus provides access to existing field equipment. We have OPC-UA, which provides semantic structure and security, and MQTT, on the other hand, also provides highly scalable architecture and efficient transport. So together, they form a communication backbone for the contemporary smart factory. And that is how all these come together in a single project. So the diversity of industrial protocols is often described as a problem to be solved. But in reality, it reflects decades of accumulated investments involving requirements and very pragmatic engineering decisions. Modbus is still existent due to the fact that it just works and it's very lightweight, even though it has a lot of security issues. Then we have OPC, which also exists because it's industrially required for structure and security. And then MQTT has also been largely adopted in recent times because it employs scalability and efficiency. So a competent industrial architect does not choose between these protocols. They design systems in which each protocol performs the role for which it is best suited. So I hope you enjoyed every bit of this. If you learned something new today, do well to hit the subscribe button. And thanks for watching. This is Boots and Bots.